Okay, so that was an intense lecture, but the bottom line is there are a number of questions associated with temperatures in welding, such as what is the cooling rate? What is the thickness of the heat affected zone? How far behind does my molten metal trail? What is my solidification time? All those questions I just mentioned can be answered with the formulas that are in these pages of formulas that I showed you, and that are also in, if you look at the old exams, in the formula sheets. For all those questions, which you need the material properties, which I have given to you. You might need the thermal efficiency, which I have given to you in this set of slides. And you would need to know if it is thick or thin or fast or slow. And there's a formula for each of those things. And you just plug the formula, done. So it's quite incredible. What I want to leave now is one problem, and then I would like to do a similar problem. I'm going to leave this one, and then that is the final of 2018, and then a very similar problem of the final of 2019. I'll split you in groups, and as you work with each other, I'm going to go visit, and I want to make sure you go through the mechanics here. So this question is, how thick is the heat affected zone in a particular weld? Here we have the travel speed. Here we have the voltage, right? We have, I didn't say here what the current is, so, but you used to know it, and I'm going to make sure we have it, right? And it says, well, what temperature to assume for the edge of the heat affected zone. Last Tuesday, this was actually one of the questions in the quiz, right? And whether this is N18 corresponds to A1, right? And if you want to calculate it using some approximate formula, we have an intermediate temperature suggested here, right? All right, so we need to determine if this is what formulas to use. Here we have the material properties. That was in the formula sheets when the exams were not open book. Now these material properties here on the left are something that is in that you have in your notes. In our case, they say typical carbon steel properties. So here we have alpha, the thermal diffusivity. Here we have the K, the thermal conductivity, right? Okay. And then to calculate the efficiency, the power into the weld, we need an efficiency. So this says use thermal efficiency for argon-rich blends, right? Okay, so we have Meg and suggests something of the order of 0.7. What is the first step in all the welding problems, all these temperature associated problems, is to know what formula am I going to use. If you those of you who took the heat transfer class, remember that before you calculate heat transfer with convection, you need to know, is it laminar? Is it turbulent, right? And we calculated the Reynolds number. Now it's very similar. This has nothing to do with turbulence, but the question is it fast? Is it slow? Is it thick? Is it thin? And we don't have now a single number like Reynolds. I can say, oh, if this is Reynolds, we're one way or the other. Now we're in a 2D space. So we need to calculate two things. One is where we are. Easy, let's start with the dimensionless thickness. And we have a formula that is in your notes. It's right here. Dimensionless thickness is travel speed times plate thickness divided 2 alpha, and alpha is the thermal diffusivity. Here, alpha. So I'm gonna walk you through this. It's gonna look very easy, but you have to do it on your own because seeing the blank sheet of paper can be intimidating until you develop some proficiency. So travel speed, that was 0.37 meters per minute, and this was converted to meters per second. D is the thickness, and the thickness was in the other part of the statement, but the thickness was 1 inch, right? 2.5 centimeters. 2 and alpha 9.1 times 10 to the minus 6. Let's see. Carbon steel, alpha 9.1 times 10 to the minus 6. So except that in this example, and it is in the final of 2018, it was complete. Except this 0.0, the thickness, we have everything. We calculated number 8. This is dimensionless, 8.471, whatever it is, right? Okay, now we need the other coordinate. So we need in this D is 8.471, right? This is 1, 2, 3, 4, 5, 6, 7, 8. So the D star is about this height. This is in log scale. And then we need to calculate the recalling. We need to calculate those two things to be in this map. The formula for recalling, we have it here. And we do power times travel speed for pi k alpha and t minus t0. So Q is actual heat into the plate. So we would have voltage times current, and I need to multiply by the thermal efficiency. Voltage, I have it here, 29.5 volts. And I'm not going to do this for the exam, but you realize that if you don't have it, you can start guessing the voltage using the formulas for voltage we already discussed, times current. And I didn't put here the current, but the current was 320 amps. And the thermal efficiency for the argon rich, we already discussed, Mig, argon rich, about 0.7. And that gives us some value of Q, right? 6.6 kilowatts. I put 6.6 kilowatts times the travel speed over the, you see, I have here 4 pi k alpha. Okay, 4 pi k, this is K for steel. Let's check it out. K for carbon steel, 41. And 41 times alpha times, you see that the formula involves a temperature. And this temperature here is suggesting use 1045 as representative of the heat affected zone. And we have minus T naught. T naught is the preheat. In this case, nobody told us anything, so let's assume that the plate was at room temperature. But if your question is, okay, how much preheat? Or I give you the preheat, here you have it. It appears in this part of the formula. When I put all this, I calculated a recalling number of 8.48. 8.48 for recalling would be, okay, let's go again. This is 1, 2, 3, 4, 5, 6, 7, 8. Here. So if I put a point that was 8.5 in D star and 8.5, what a coincidence that is so similar, right? And 8.5 for the recanding, the point falls right here. If the point falls right there, that means our weld falls into the fast and thick regime. And I will need to, I'm going to make a note to myself. I fall here and fall in fast and thick, right? Every question I have about this one weld, I will be using the formulas that correspond to regime 1. Every question you ask me now, I know I'm fast and thick. All right? And this is part of what was the formula sheet in the exam, but it's also in your notes. And you have the exam. And any question I ask you, you would go, okay, what question it is? I use the formula that corresponds to 1, whatever I ask you, whatever actually happens, you happen to need in your professional life. If you landed in 1, there you go with 1, right? And the question was the thickness of the heat affected zone. And for that, we have a formula, right? The delta Y, that means the thickness between melting and between melting and A1, right? And here we have, look, we have Q, which we just discussed. We have alpha, 2e pi, this is like, E is e to the 1, right? 2.71. Thermal conductivity, travel speed, melting temperature, and temperature of the heat affected zone, that is the A1. And here we have this intermediate temperature that that I gave in the statement, and the preheat temperature. So I copied that thing here and I rewrote it. Q we had already calculated, 6.6 kilowatts. These are 6.6 kilowatts of Q we had calculated. Times alpha, right? Which it came straight from the table. 2E, again, in all scientific calculators, E is the Euler's number, e to the 1, pi, K, thermal conductivity, is 41. U is the travel speed, which we have determined. And here we have this other melting temperature. And look at this. Melting temperature for carbon steel, they give us 1800 in Kelvin. Nobody uses Kelvin. I don't know why they put it in Kelvin. Probably they felt more scientific. But people using imperial units don't use Kelvin, and people using Celsius don't use Kelvin. And those using Kelvin don't use welding. So anyway, we have 1800 Kelvin. There is a melting temperature, minus 273. So we turn it into degrees C. And 718 degrees C for the edge of the heat affected zone, right? But that depends alloy by alloy, right? But this is a typical value for A1. And below we have an intermediate temperature that I suggested 1045, and can be some sort of average between these other two temperatures, melting and edge of heat affected zone, minus preheat. That was 20. Nobody said anything to it, 3/2. You do this calculation, and that gives you a thickness of heat affected zone 2.9 millimeters, almost 3. Actually, pretty good estimation. It tends to be like that. So What have we done? For the number one thing I need to do is determine where I am in a map, right? And for that, I need to know where I am in a map. I need two coordinates. One is dimensionless thickness, that is this D star, and the other is the recalling number that has the more complicated formula. But those two are here. Based on those two, I would know where I land. And based on where I land is which of these formulas I would use. Right, and here we have regimes 3 and 4. Regime 3 is thin and fast. Regime 4 is slow and thin and slow. Right, thin and slow. That's correct. Right, it depends on what they are asking us. Are they asking us about T85? Are they asking us about solidification time? Are they asking us about thickness of the heat affected zone? Are they asking us about cooling rate? No, cooling rate is not there. Where is cooling rate? Here, this is cooling rate. Okay, what I would like to do now is, I believe everybody, can somebody confirm that I sent an email with the final of 2019 attached? It's not the formula sheet, it's just the final. I would like to do that together with you. So please let me know if you got it or not, because that's what I would like to you to do, and I'll be moving through the different groups and see how you're doing.